Imagine a pipe carrying liquid sodium at approximately 500 degrees Celsius. This liquid must move through a cooling circuit at the flow rate required by the system. Yet a cross-section of the pump reveals no impeller, rotating shaft, or rotor. No internal mechanical component pulls or pushes the liquid forward. The casing appears almost completely motionless while the stream of hot metal continues to move. It sounds like a pump with its most important component missing. But in an annular linear induction pump, or LIP, the material playing a role similar to a rotor is the electrically conductive liquid itself. The pump does not transmit force through a rotating shaft. Instead, it creates an electromagnetic field that travels along the pipe and applies force directly to the sodium. So how can stationary coils produce enough continuous thrust to turn a column of liquid metal into a pressurized coolant flow without any rotating mechanism inside the pump? Sodium works with this mechanism because it conducts electricity. When liquid, in a sodium-cooled fast reactor system, the coolant absorbs heat from the core region and transfers that heat to a heat exchanger. Depending on the specific system design, an electromagnetic pump can maintain circulation without requiring a rotating shaft to pass through the boundary containing the sodium. From the outside, an ALIP resembles a thick section of pipe surrounded by circular coils. But its cross-section contains three principal regions. At the center is an inner ferromagnetic core. Around that core is an annular flow channel through which the sodium passes. Outside the channel are the magnetic circuit and the multiphase coil assembly. A sealed pipe wall separates the sodium from the electrical coils, so power is not supplied directly to the liquid through electrodes. The annular shape is not simply an unusual pipe geometry. The inner core and outer magnetic circuit guide, concentrate, and close the magnetic flux path through the thin layer of sodium between them. The coils are arranged sequentially along the axis, making the pump resemble the stator of an induction motor that has been opened and laid out in a straight line. But a magnet does not simply pull sodium along the pipe. Sodium is not driven forward merely because it is a metal. To generate directional force, the system must produce both a traveling magnetic field and an induced electric current inside the liquid itself. The first obstacle is that a stationary magnetic field cannot sustain this induction pumping mechanism. If the field does not change relative to the sodium, the required induced current diminishes. Therefore, even though every coil remains fixed in place, the magnetic field pattern they produce must travel along the pump axis. The second obstacle is the velocity difference. The magnetic wave has a synchronous velocity determined by the electrical frequency and the spatial arrangement of the coils. The sodium must move more slowly than that wave, so relative motion remains. This difference is commonly called slip. If the liquid velocity approaches the synchronous velocity, induced current and electromagnetic thrust decrease. But increasing slip does not create unlimited efficiency. Electrical losses, Joule heating, and end effects at the boundaries of the coil region also become important. Temperature creates another obstacle. The sodium must remain liquid, while the electrical windings and their insulation cannot be heated without limit. Some systems require a preheating mode to melt sodium that has frozen inside the piping, and coil temperatures must be monitored during operation. Bearings and dynamic shaft seals are absent, but electromagnetic and thermal limits remain. So how do engineers create a magnetic wave that moves along a stationary pump? And how does that invisible field become real pressure inside the sodium? The answer begins with three-phase alternating current. Three groups of coils receive currents displaced from one another in time. Each group produces a magnetic field that rises and falls. Because the groups do not reach their peak simultaneously and arrange sequentially along the pump, their combined fields form a pattern that travels along the sodium channel. No physical object moves through the windings. What moves is the position of the electromagnetic field peak. As this magnetic wave sweeps past the electrically conductive sodium, the magnetic flux experienced by the liquid changes. Electromagnetic induction then produces eddy currents within the sodium. Their direction opposes the change that created them, so they depend on the relative motion between the magnetic wave and the liquid. The two required components now coexist within the same volume of liquid, induced current density J and magnetic field B. Their interaction produces Lorentz force density, commonly represented as J cross B. With the correct geometry and phase sequence, the useful component of that force points along the pump axis. This is not an impeller pushing separate layers of sodium from behind. Electromagnetic force is distributed throughout the volume of liquid under the active coil region. It produces a pressure gradient. Outlet pressure becomes higher than inlet pressure, and that pressure difference drives sodium through the rest of the circuit. And a LIP can be understood as a linear induction motor whose electrically conductive secondary is not a solid metal bar. It is the liquid sodium itself. The coils act as a stationary stator. The electromagnetic field is the moving pattern, and the liquid both receives the force and becomes the output flow. This comparison remains accurate only when the goal is understood correctly. The pump creates a pressure rise in a liquid. It does not rotate a mechanical rotor. The voltage and frequency supplied to the coils can be adjusted by an appropriate electrical drive. Changing frequency changes the velocity of the magnetic wave, while changing the electrical supply conditions changes field strength and pump behavior. Actual flow also depends on the hydraulic resistance of the complete circuit, the electrical properties of the sodium, channel geometry, and losses within the pump. An electrical control setting does not translate into one fixed flow rate in every system. Now, the complete operating chain can be assembled. Multiphase electrical power enters the coils. The coils create a magnetic field that travels along the pipe. That field induces electric current in the sodium. The induced current and magnetic field interact to generate Lorentz force. The distributed force creates a pressure rise, and that pressure rise sustains sodium flow through the cooling circuit. In a representative circulation loop where this pump type is selected, sodium can leave the region where it receives heat, travel to a heat exchanger, transfer energy to another circuit, and then return. The pump does not cool the sodium. It supplies the pressure difference needed for the liquid to transport heat. Thermal energy is carried by the sodium flow, while electrical energy is converted into pumping force through the electromagnetic field. The mechanical benefits are clear. There is no shaft penetrating the pump body, no impeller rotating in the sodium, and no dynamic shaft seal at the pump assembly. The liquid boundary can remain hermetically sealed without a rotating shaft penetration, reducing the number of mechanical parts exposed to wear. This is why electromagnetic pumps are attractive in liquid metal systems, where sealing and reliability are highly valuable. But no moving parts does not mean no losses or no need for protective engineering. Induced currents also produce heat. Leakage flux and end effects reduce useful force. The pipe wall, magnetic cores, coils, electrical insulation, and any required thermal management system must all operate under severe thermal conditions. And a LIP exchanges one set of mechanical problems for a set of electromagnetic, thermal, and materials engineering problems. So how does an impellerless pump drive liquid sodium? It uses three-phase current to create a traveling magnetic field. That field induces electric current in the conductive sodium. The interaction between induced current and magnetic field produces an axial Lorentz force, creating a pressure rise that forces the liquid metal to circulate. There is no hidden mechanical rotor inside. The first thing that moves is an electromagnetic field pattern, and the material that directly receives the force is the liquid. That is how a sealed section of pipe can perform the work of a pump. It converts electrical energy into pressure without an impeller, rotating shaft, or moving mechanical component in the sodium flow.